This is the most basic equation of eigenvalue and eigenvector. Although it looks simple, they help us analyze stability in engineering structures, understand vibration patterns in mechanical systems, and even enhance technologies like facial recognition. In this video, I'll be diving into the core concepts of eigenvalues and eigenvectors, explaining them in a simple and relatable way. After that, I'll demonstrate a Python-based application where you can see how these mathematical concepts come to life in real-world scenarios. Let's get started. Imagine you're standing in front of a mirror. Most things look flipped, but if you point straight at the mirror or straight away, your finger stays in the same direction. It only moves closer or farther. Eigenvectors work the same way. They are special directions where a transformation only stretches or shrinks the vector but doesn't rotate it. The amount of stretching or shrinking is called the eigenvalue. The fundamental equation is this, where A is a square matrix, V is an eigenvector, lambda is an eigenvalue. This means when matrix A acts on V, it only stretches or shrinks it but doesn't change its direction. Okay, let's get into a little bit of math. To find the eigenvalue and eigenvector of a matrix, we first subtract lambda V from both sides of this equation. Then we insert a unit matrix I between lambda and V. This is the matrix equivalent of multiplying by 1, so the equation doesn't change. If we factor out the vector V, we are left with V times A minus lambda I equals 0. If V is 0 here, the equation is meaningless. What if our matrix A minus lambda I is invertible? If this happens, our V is indirectly equal to 0. So our matrix A minus lambda I has to be a non-invertible matrix. Following the rule of non-invertible matrix, the determinant of this matrix is equal to 0. Let's solve an example problem. A is a square matrix, so the determinant A minus lambda I equals 3 minus 4 lambda minus lambda square. From the equation we get lambda, our eigenvalues, 1 and 3, and the eigenvectors are any non-zero scalar multiples of these. Okay. Now I want to show you the geometric meaning of our example eigenvalues and eigenvectors. I wrote this code in Python using the matplotlib library, and I use same matrix set here. Let's run it now. Let's see. Here I applied a simple symmetric linear transformation. The purple and blue lines show the eigenvectors, multiplied by a big number for convenience. Now these blue and purple vectors are parallel to these eigenvectors, so their directions do not change. The length changes because the eigenvalue of purple is 3. The red vector is not parallel to any of them, so both its length and direction change. At here I want to create a weather simulation where each day can be sunny, cloudy, or rainy, and the next day's weather is determined by a probability matrix. The goal is to predict the long-term weather distribution. I use Markov chains and stochastic processes. The daily transition probabilities could be this. For example, if today is sunny, then tomorrow has a 70% chance of being sunny, 20% chance of being cloudy, and 10% chance of being rainy. I have randomly simulated 1000 days of weather with the given probability, and I will compare the steady state I found using eigenvalues and eigenvectors. The answers are very close to each other. This indicates that the validity of the answers we get using eigenvalues and eigenvectors is great.